Hello, everyone. Welcome to our webinar today. This webinar is being presented by Clean Energy Group, and the topic for today's webinar is Solar and Battery Storage Fire Safety Part 2, Utility Scale Projects and EVs. And we have an excellent guest speaker with us today, but before I pass it over to him, I'd like to go over a couple of webinar logistics. All attendees are in listen-only mode, so your webcam and microphone are disabled. The chat function is disabled. We will not be answering questions through the hand-raising function. We will be, so if you have a question or a comment, you can submit it via the Q&A panel, and we'll be saving 15 to 20 minutes at the end of the webinar to address audience questions. So if you have a question during the webinar, just pop it in the Q&A box, and we'll get to it at the end. Automated captions are available, and the speaker's bio will be made available in the chat. And finally, this webinar is being recorded. We will email you a webinar recording within 48 hours, and it will also be posted on CEG's website at cleanegroup.org/webinars. And with that, I'd like to pass it over to our host for today, my colleague Olivia Tim.
Doreen, and hi everyone, welcome to this webinar today. This webinar is a presentation from the nonprofit Clean Energy Group. We're a national nonprofit advocacy organization working to advance the transition to affordable, reliable, and clean energy for all. A few of our project areas include climate resilience and community health, distributed energy access and equity, energy storage and flexible demand, and how we can replace fossil fuels with renewables. And I'd encourage everyone to go to our website to learn a little bit more about this work. That's cleanegroup.org, listed on the bottom of the slide. Check out our different project tabs. One to highlight is the Resilient Power Project. CEG established this over a decade ago to support communities that are advancing solar and storage projects and to build local resilience. So through this work, CEG provides technical assistance support for local resilience. And in the coming months, we'll be supporting community solar and community solar plus battery storage, and additional community benefiting projects. So again, if you're interested in learning more, visit our website, or you can reach out to us directly. Next slide. I believe you'll see some statistics about this work. Over the last 10 years, we've been able to award over $2 million in technical assistance grants, worked with over 200 community service partners, and done work in over 360 community facilities. Slide. So today's webinar is part 2 of our battery storage fire safety series. So we hosted part 1 back in June, which focused more on residential and small commercial facilities. So today, I'd like to welcome back Captain Richard Burt, who is a retired fire captain. He's got over 30 years of experience in the fire service. He's also the founder of Solar and Fire Education, which is an organization that provides free training to firefighters across the world. It has information about how to safely mitigate fires involving solar and battery storage. So today's webinar will focus specifically on larger utility scale storage, but it also will touch on electric vehicle infrastructure. The course will be very detailed. So the course that he presents normally to firefighters is very detailed. It's 6 hours long. So today we won't be able to cover everything that he talks about, but we'll hear an overview and we'll get some highlights about this topic. So if you are interested in talking with Captain Burt more about the full course, you can reach out to him by email, and I can put that in the chat for anyone that is interested. But his email is solarandfireeducation@gmail.com. So that's for if you're interested in the full 6-hour course for a fire department. All right, so after this presentation, we'll take all of the questions that we have time for. Like Zareen mentioned, please put those questions in the chat as they come up, and we'll get to as many of them as we're able to after Captain Burt's presentation. So with that, I'll hand things over. Thank you, Captain Burt, and welcome.
Thank you, Olivia, and great to be with everybody again. I've got a short period of time to talk about a lot of stuff, and so super excited. Again, I spent 30 years as a firefighter, but I was an early solar pioneer. And I want to start with this first slide just to explain a little bit of my background and why I'm doing this training across the world for firefighters. If we go to that next slide. So basically what happened was I was living off the grid, guys, with solar and batteries, and built a home up in the mountains outside Las Vegas, and very successfully living off solar and batteries. And what happened was Nevada Energy got upset with net metering and tries to shut the whole industry down. And what we did is basically back then we started talking about, in the early 2000s, actually talking about resiliency for communities and how solar and batteries are good for disasters and are good for the community in general. And we led this campaign, and we basically brought back solar to Nevada, went straight through the government. And so it was a really proud moment for me to work with the solar industry to show that solar and batteries are going to be critical for our infrastructure in this world, in this country. And that's where I want to start this. So with the new tax levy and with the new tax code, we're looking at basically large storage, and we're looking at large solar farms connected to storage as going to be part of this community, as part of the infrastructure. So let's dig into that. Let's go to the next slide. So basically, you can't separate large solar field with batteries because that's what they're doing. They're putting these together. And so when I teach in Europe, I talk about basically the solar side and the battery side, and it's interconnected. And the one thing we have to understand is that if we start putting solar panels on all our real estate, on all these buildings connected to large storage, whether it's the facility or it's an isolated area with large storage containment units, basically what we're looking at is fundamentally, can we keep everything safe to the standard which the grid is at currently? And so that's where strategies and tactics for firefighters is critical. So this I teach in Europe because there is no rapid shutdown. We're ahead of the game in the US. Again, we get a grade A for our rapid shutdown, which we have integrated into commercial solar and basically residential. And I want to highlight this because this is fantastic where we're starting compared to Europe. So when I talk to Europeans, I talk about firefighter safety, civilian life safety, incident stabilization, and property conservation. Those are critical with what we've already done. So let's go to the next slide and start digging into why we've done this and why we've done a good job doing this. And going forward, we will continue to build on this resiliency and build on this tempo of getting clean energy in a community, and it works and it's safe. So I show this slide because this is the building blocks again of the solar side, these MC4 connectors. And where we're seeing fires is in these arcs where there is basically a loose connection in a large solar field or on a commercial building. So if we go to the next slide, you've got these building blocks. And what happens is if you have a solar array on a large commercial building and you have no way of rapid shutdown, which we didn't, till we changed the code and said on a commercial building, you now have to have rapid shutdown. Basically, what we were looking at is if there was any damage or an arc happened with one of those MC4 connectors, you're looking at 4,000 degrees Celsius, an arc that is not shutting off during the day, and that's why we're having the fires. So having this rapid shutdown got eliminated this part of the problem. So you have just a string with a high voltage inverter. If you have any of those connections arc on a rubberized roof, which usually a commercial roof is, basically what we're looking at is a fire starting. We've got past that with our code. So if you go to the next slide, here's a microinverter optimizer. You put it on a commercial structure. Now you have that arc fault protection. So if there is any kind of disruption or there is an arc, especially at those MC4 connectors or at the high voltage inverter, we get rapid shutdown, which again is that built-in safety for large commercial. We can't do that on solar farms because it doesn't pencil out financially, but actually covering all our real estate in panels connected to large storage is a brilliant idea. And the idea of having rapid shutdown with that is what we've got to continue. And I've got to continue telling the solar industry, this is a brilliant way to go. This is the way to do this safely for firefighters, for civilians, for buildings, and for the investment in it. So if we go to the next slide, with arc fault detection, it's getting better and better and better. What's happening is, again, America is leading, the solar industry in America is leading that charge on arc fault protection. So when an arc does happen, how quickly is this arc going to be picked up? And will it create the heat to start a fire? So I want all the industry that are listening in, think about what you've deployed, think about all those connections, think about the high voltage, and what kind of safety have you built in for that arc fault protection? Because that is getting better and better. And what we're looking at is being proactive on rapid shutdown, whether it's an optimizer or a microinverter. That is the way to go for a very large commercial system, especially on a piece of real estate that can burn. Whereas in a field, and I'll talk about solar farm, we don't have to worry about that. We have to worry about grass fires and losing the asset. So let's go to the next slide. So here's a good example of a commercial building. They had an arc. There was no rapid shutdown. So this is where I use an example to say to the industry, listen, we've got firefighters. I train this department. I know this department very well. I know the incident very well. And what happened was they got on the roof. There was no arc fault protection, and it started to grow. The fire started to grow. With simple strategies and tactics, we go to the next slide. They managed to put the fire out. But what we found from the fire inspection and the investigators was it was an arc fault at a high voltage inverter. Again, this is what I use for key guidance for the solar industry to think. Cover your real estate with solar panels. Please do that. Connect it to large storage, which is right there in the community. It's a great way of doing it. But you've got to think about all those thousands of connections and the high voltage, and having an arc fault protection system with rapid shutdown is key. Go to the next slide. So at this point, you've got damage on the roof, and basically you've got to start working out, is it worth the money to put into arc fault protection? Is it worth the money for optimizers or microinverters? Because they make optimizers for commercial and they make microinverters for commercial. Start looking at that, not just in the residential market, but in the large commercial market that's available right now connected to storage. I'm doing lectures where fire departments have reached out to me and said, Rich, they're putting a whole bunch of large storage in the campus with connected to solar panels that cover the entire area. And so those are interconnected. There's not a separation between those two. So really start looking at, when you put large storage in, do you have microinverters? Do you have optimizers? And do you have arc fault protection? And what does that look like? And is that cost initially worth the cost? When I start looking at fires like this, I'm saying to the solar industry, yes, it's worth the cost of arc fault protection for large commercial on a building. Okay, let's go to the next slide. So connected to batteries. This is where we're going to dig into batteries. And this is the interesting part. They want to put large storage into communities. Where and how? And EVs are everywhere, millions of EVs. So I've got to start teaching the fire department. You've got a different energy source, and this is critical to understand for firefighters. And I'm going to give you the firefighter perspective. Is the solar industry wants to put large storage in. Where do you put it? We're not talking about residential storage. We're not talking about 1, 2, 3 power walls or an Enphase battery or an LG battery. We are talking about large storage. And where does it go? And what does it mean to the community? And what does the fire department do if there is a failure? Where it starts with chemistry. It starts with understanding what's in the box, where it is, and what to do with it if something happens. I teach that there's hundreds of lithium-ion batteries in circulation, and it doesn't have to be large storage or an EV. In a house, you must be got 10, 20, 30 pieces of equipment in your home that have lithium-ion batteries in them. We have to be aware that these are everywhere. We've been using them for years. It's just now we're putting them in a concentrated load. That's the difference. So if we go to the next slide, basically, what is the cell? So to clear things up, I've got some notes here, and I want to add this from the last class because I had a great question, and they said, Rich, what is the chemistry being used right now by Tesla for a residential battery and for their large storage. And so right now, again, the industry has done a great thing and went to LFP. So basically right now, the industry, lithium iron phosphate, LFP, is the main chemistry used in residential and basically in large storage. Now, the EVs are completely different. That's NMC and NCA chemistry, and it has to be that chemistry because it makes a car go fast, okay? So at this point, I want you to understand that most of the cells being created are LFP. Now, the advantages of LFP are that they aren't as dangerous as NMC and NCA. That's why we shifted to them. And I'll talk a little bit about why. But let's look at that. So to give you an idea of how much circulation these cells are, basically Tesla has some numbers out, and Tesla made their 4680 cell. They make an 18650 and a 4680 cell. They made their 100th millionth cell in September of 2024. So these are in circulation. We've got to understand how they work. And basically, you have an anode and a cathode. And an anode's negative and the cathode's positive, and there's some electrolyte, and it moves back and forth, charge and discharges. And so it's a very genius way of storing and supplying electricity. The question is, what's in the electrolyte, what's in the anode, and what's in the cathode, and where are the problems there? So let's start digging into that. So let's go to the next slide. So we're going to concentrate on lithium, nickel, manganese, cobalt oxide, and lithium, nickel, cobalt, aluminum oxide, and LFP. Those are the basic fundamental chemistries that a firefighter is going to see. They're going to see some other chemistries, but this is fundamentally, you got to remember that 100th millionth cell that Tesla made. So at this point, this is the most common cells. So we've got to start digging into these different chemistries. And basically what we're looking at is, if you have large storage, what does it mean to a community? I hear nightmare stories all the time about large storage and the smoke. And if it's burning, do you let it burn? Do you put water on there? Is the water contaminated? So at this point, what I want to start talking about is what we're facing as a fire department. If large storage is put in a community or near a community, what does a fire department need to know? Where do you place it? And what are the dangers? So let's go to the next slide. So again, I use this slide because it's a great slide to show basically LFP is used in large storage. There are some NMC and some NCA chemistry in large storage. The fire department should basically identify it and know where it is. But most of the new storage is going to be LFP. So what do we look at LFP? We say, okay, so the thermal runaway temperature is 270 degrees Celsius. So at this point, it will burn. Basically, the cell will become compromised, and you'll have basically cells burning, and you'll have hundreds and thousands of those cells burning. What I'm teaching the fire department is this, and it's very, very clear from the training we've had. If you have one of these storage facilities on fire, and basically you have 10, 20, 30 of them, and maybe 10 feet apart, 5 feet apart, your job in the fire department is to let that one large storage burn. So if it's on fire, keep it burning because of what the products of combustion come off those. So there's a lot of hydrogen and there are a lot of gases. If it's burning those gases. So, and lithium doesn't react well with water. So at this point, and where are you getting the water source from? Because the solar industry is doing a good job of identifying where to put batteries to. So large storage batteries are being put in areas where there may not be hydrogen water. They may not be able to get water to that site. And so flowing masses of amount of water trying to fight one of these batteries is actually non-productive. So teaching the fire service to stay away from the battery that is affected, let it burn. And the biggest thing they can do for that community is to protect exposures. This is the thing that fire departments want to do. They want to put wet stuff on the red stuff. If there's something burning, they want to put it out. That's our instinct. So teaching them that basically this chemistry is much better if you let it burn. Again, you've got to look at the plume of smoke. So for LFP, yeah, you've got some hydrogen in there, but guess what? It's lighter than air and it's dissipating. If it's in a container, then that's a different story. So if you've got hydrogen in a container, so the industry, I've noticed too, is doing this. They're basically putting containers out. So when they vent to the outside, and they're a simple container that can vent and burn. We've got to protect the exposure. So this is where the fire department has to understand that we don't go straight to the flames. We look at the site and we say, okay, how do we protect exposures? Because at 150 degrees C, if you have a container next to the main large container and it's on fire, guess what? You can start having off-gassing and you can start basically producing thermal events in that next one. And then you have a cascading event. So it's critical for me to spend a lot of time with firefighters saying, set up a water supply, but you're not setting up a water supply to extinguish that battery. What you're doing is you're setting a water supply up to protect exposures and monitor which way the air is flowing, which way it's going, and shelter in place. And do not make entry into a system that has batteries in it, but does not have ventilation. So these are just critical, straightforward, fundamental things that a fire department can pull up on scene, contain the fire, as in protect exposures, let it burn, and basically stop the scene from escalating, keeping personnel safe, realizing the gas has come off. And as I said, when it's vented, it's very, very safe where the hydrogen is being released, especially with LFP. Now, NMC and NCA, again, critical not to put water in there for fundamental reasons of there's heavy metals too in the smoke. So at this point, the shelter in place is critical to understand which way the plume's going, if there is smoke, and shelter in place and let it burn actively so it burns out the chemistry in those cells. So if we go to the next slide. Now, the testing is interesting because they always talk about testing and they say, how are the cells tested in the fire? And UL 9540 is a very good test, but they test it at a unit level for residential. At the large storage, they've done very little testing at that size. What they've done is they've done cell testing. So if you go to the next slide, they'll show the cell testing that is done. So that's the important thing is we'll break down a container that has thousands of these cells in it. And we can say, okay, this is what this cell's going to do. Where if there's lots of them in there, we can start building basically what's going to happen. And so if you burn a cell for 9548, you have all this information. And the information is great because it's showing us, number one, it's got to be ventilated. Number two, if it burns off, it starts basically getting rid of all those off-gassing. And number three, we want to protect exposures. So instead of complicating the issue, and for firefighters turning up on scene and say, what do we do? Water on it? We don't. This is the critical thing to understand. Okay, break it down to the cell level. We have a cell. What's that cell going to do? It's going to propagate to the next cell and the next cell and the next cell in the box. Okay, we can't do anything about that propagation right now. We can't. It's going to burn. Okay, so we've got this burning cell. It's producing this, and now we have all these cells on fire. It's producing heat. It's producing flames, and it's producing these gases. Okay, are those gases collecting or are they dissipating? Next question. Okay, and if there is a plume of smoke, which way is the plume of smoke going? Number four. Okay, how do we protect the next one from not catching on fire? How do we set up a water supply? How do we basically cool that next unit? And so I'm looking at products. I did some fire testing up in Ontario, and they have a product. It's called Fire Rain, where what I'm looking at testing is this. You have a large storage and it's on fire. Fire department pulls up. Let's say this large storage area that has 200, 100 large batteries, 10 feet apart, 5 feet apart on concrete pads. and one's on fire. And it's not the one on the edge that always catches fire, the one's in the middle. How do we do this? How do you set up a water supply to protect those exposures? We know what to do now. The fire department's got it. Okay, Rich, we let it burn. We protect exposures. We look at shelter in place. We look where the plume's going. We realize a lot of it's dissipating. It's vented. We're not making entry. Where do you get the water to continue a water curtain for 2-3 hours of continual burn on the battery? So these are the questions that come up. And so one product they looked at is a gel, and it will stick to metal. And basically what it does is it's got a cooling property. So what you're doing is you basically pull up on scene, you've got the burning battery, it's vented, you've got the plume, you're working out which way the smoke's going, and what you're doing is you're coating the area, the other cells, with the gel. And what I'm finding is you don't have to do a continuous flow. If you think water hitting metal, it's just going to run off, and you've got to continue that spray. You can't just stop, let it heat up. The gel, you cover everything and you monitor it with a thermal imaging camera, and basically you can tell when that surface, that metal starts to heat up. You know what it is. 150 C is a great indicator. With our thermal imaging, we've got it down to pinpoint. You can pinpoint spots, so you can start monitoring those other exposures. And what you're doing is not flowing water continuously. You set up the line, you cover the exposure, and you wait and monitor. If you need more, you cover the exposure and wait and monitor. And it changes the game for me, how I think about it, of the most important thing for fire departments is setting up a water supply and cooling and exposure. Those are the hard conversations because the infrastructure is not there. And it's really hard for a developer, a battery developer, to put in that kind of amount of water infrastructure. Think about where they're going. So to me, also, if these are closer to a commercial building, if they're closer to a community, number one, we've got to think about which way is the plume going. Number two, protecting exposures of buildings, protecting exposures of other battery systems is going to be critical if it's closer. That brings me to EVs. EVs is the same idea. You've got an exposure. You've got basically thousands of cells in a car, and it's not a residential battery, and it's different chemistry than a residential battery. So at this point, the residential battery and the large commercial storage is mostly LFP. The cars are different. Let's go to the next slide. So at this point, what does the NMC and NCA chemistry, not LFP, have in it? So when you look at an e-bike scooter, when you look at a car fire, that's an EV, what's burning? So this is where we have to be really, really smart about the smoke that's coming off an EV or even the small lithium-ion batteries in your home. And you have about 20 of them. If every one of you got up, you would identify 20 of these different batteries. So if it's NMC or LFP or NCA, we're looking at some very, very toxic smoke. Now, LFP is toxic smoke. You don't want to breathe it in. But the trouble is, with these older batteries and these older chemistries, we're looking at some heavy metals for contamination. Again, that's why we've got to be careful how much water we put on these and basically what's in the vapor. And so we're finding basically what we've got to fundamentally do is understand the cell. We've got to understand the chemistry. We've got to understand that burning is better than trying to put this out, and that exposure protection is going to be very, very important, and obviously arc fault protection. And all these things have to be looked at continuously, studied. Every event that we have, we've got to look at, did they have those factors? So let's go to the next slide. So thermal runaway, basically, why are large storage failing? And so we have this large storage facility catch on fire. Why? Well, we've got to look at what causes cell to fail. Now, there's mechanical abuse, and in an EV, again, this wraps up why EVs, they're driving down the street, you're banging the curb. Basically, you've got a cell in an EV and it's getting knocked around. So this can be mechanical abuse very easily on a traffic wreck. Electrical abuse, charge and discharge cycles. Are they mellow or are they hard charge and discharge? Think about how many kilowatt hours go into one of those superchargers on a car. There's a lot of abuse on those cells. Then there's thermal abuse, obviously, if there's a fire. So what we look at in the fire service is start understanding what are the abuses of this cell. So instead of standing around the fire department, I'm teaching the fire department this. No longer stand around and go, wow, they said this wasn't going to catch on fire. Let's be logical about it. Is it mechanical abuse? Was it electrical abuse? Was it thermal abuse? If you go to the next slide, these are questions the fire department will start asking, and having an educated approach to this is so much more important. So on the next slide, basically on large storage, we have found dendrites. And what they are is over time, you basically have a stalagmite or stalactite forming in the cell. It can pierce the separate and you can have arcing. So we're finding out different reasons why. But the thing is, the fire department doesn't have time to sit there and say, well, this was not meant to happen. It's just like the electrical grid. When we turn up on a transformer fire, we don't stand around and go, well, this was not meant to happen. Why did it happen? It happened. It happens. And we're finding out why. The question now is, can we logically approach this with strategies and tactics? And can we fundamentally solve this problem instead of causing basically a vacuum of, well, we don't know what to do because they said it wouldn't go wrong. No, we're at a point where this is going to be critical infrastructure and stuff goes wrong. And so I use the analogy of elevators in Las Vegas. I was on a heavy rescue. You know how many elevator rescues we did? Because the elevators went wrong. The thing is, we knew what to do. So at this point, what we're looking at is let's fundamentally look at the problems. They can happen, but then let's look at the strategies and tactics. If I get a fire department to approach a scene with large storage and say, okay, we've got cells, thousands of them. What's the chemistry? What's the thermal runaway? What do you think may have happened to that? And fundamentally, what is the smoke? Do we let it burn? Can we protect exposures? And basically run that scene in a very, very logical way. We're looking at solving the problem. This isn't becoming a large problem. Now, if you turn up on scene and you start putting thousands of gallons of water on lithium or on NMC or NCA chemistry with heavy metals and start soaking the ground, and you've got thousands, hundreds of thousands of gallons of runoff, and you're not putting the fire out, and it gets worse, and you're not protecting exposures, and you're not thinking about the smoke, then you've got a scene that's going to go south. You've got a scene that's a problem. We can solve this with very, very simple training. Like I said, my class is 6 hours. We get into the weeds so we can respond and do the right thing. Let's go to the next slide. So again, I put this slide up because we are talking about gases that are very, very explosive. So even with LFP, it's very explosive. We've got to really give respect to this. So to me, this large storage industry where they put individual battery packs and basically build not an enclosure around it. So what happens is basically you have a set of cells, their modules into a battery, and it can be vented and it's on its own sitting on a concrete pad, and you have another one next to it and another one next to it, and not enclosed in a building is the future for large storage, because we've got to respect basically how much gas and how explosive it is, and that if we let those gases out, there is no danger for explosion. That is the critical thing to understand with large storage. So at this point, understanding and respecting how explosive these gases are and guiding guiding how we deploy storage is important. The one caveat I have is an electric vehicle can put off a lot of this gas. And what if you park it 3 floors underground in underground parking? That's the big question that we're looking at now. Think of that. Look at that chart. those two charts. Give that respect. Think about a car, 3-4, below grade, parked in a parking structure that is off-gassing copious amounts of this. Let's go to the next slide. So, again, LFP, it's got a lot of hydrogen in it, guys. Yes, it's very explosive. Yes, fundamentally, the idea of large storage being out on a concrete pad that can be vented, and each storage container can be protected if it's not on fire for exposure protection, is a very, very simple layout for firefighters. Once it's contained, it's a completely different story. Once you're collecting 48% and above hydrogen, now you're talking about problem. Now, where do you approach it from? How far away? Your mitigation strategies and tactics change. So knowing that, the industry is doing a great job of individualized containers sitting next to each other. And again, it's exposure protection. Whereas the NCA may not have as much hydrogen, but it's got a lot of toxic gases in it. It's still very, very explosive. That's where we've got to really have the conversation about the electric vehicle and how much gas it gives off and where is it collecting. Because on a roadway in California and an EV's on fire, you can just let it burn. Be conscious of where the smoke's going, but you can let it burn. In a garage, 2 floors down, that is not venting, that's collecting. So let's go to the next slide. So just to give you an idea of an EV, because I talk about large storage is fairly easy to teach firefighters. Number one, most of them have seen large storage because it's becoming that prominent in their first ins. And a lot of time the solar industry does a really good job in outreaching, but they describe it to me as a metal box with a bunch of these cells in it, right, Cap? I'm like, pretty much. And that we're not going to put water on it. Yep. And the gases that are coming off are poisonous and explosive. Yep. And we're going to see where they go and do the shelter in place. Yep. And we're going to try and protect exposure. Yeah. It's a fairly simple conversation. Guys, large storage is a fairly simple conversation. Shelter in place, protect exposures, let it burn, be conscious of an explosion event if it's contained. But car, you've got thousands of these cells, guys, in a car. The trouble is that thing's moving around. It's not in one spot. And it's getting mechanical abuse. It's getting thermal abuse. It's getting electrical abuse. So at this point, we've got this moving target now. And that's the problem. That's where we've got to sort out, where do we put the moving target? So we've fundamentally got to start asking, this isn't a residential battery. Residential battery sits on a wall, minds its own business, and gets charged nicely by solar and discharged nicely by solar. It's kept at a fairly good thermal temperature. It's pretty much easy living. This isn't. Think of the abuse on a car. So at this point, we've got to fundamentally take that chemistry, take the cell, take the injury to the cell, and I'm actually teaching mechanism of injury of a cell to a car. Now, I went to paramedic school in 1992, and we were taught mechanism of injury to the patient. You pull up on scene, you look at the mechanism, and you're landing a helicopter even before you've seen the patients because you're looking at the combined speed and the kinetic energy. It's physics. We've got to start doing that with the mechanism of injury to the cell of the car. So at this point, we've got to fundamentally say, is there damage to the cell? Is there any off-gassing? Is it going to go into thermal runaway? These are critical questions. The trouble is, it's a moving target. It's not a simple question. Think about it. Think about large storage. Fire department pulls up, knows where it is. Those simple questions they got to ask. What if this car is 3 floors below and it starts off-gassing and going into thermal and filling a parking garage up with an explosive gas that you have to respect? What do you do then? These are hard questions. This is where the fire department's asking, do we ventilate? How do we ventilate? How do we enter to stop the event from happening if it starts? And if it starts, are we going to put water on it? Can we put it out? Or are we walking into a very, very explosive, toxic atmosphere? When the car's on the road, pretty much a car's on the road, you've got options. When a car is in a building, it's a completely different thing. So at this point, there's some old storage in a building. There are old storage in buildings, but the fire department are aware of that and standing back. I don't know if a fire department can pull up on scene with a car parked 3 floors below and say, okay, we're going to stand back. We're not going to do anything because of the explosive nature of the gas. We don't know if it's vented. We don't know if it's in thermal runaway. We have no idea. It happened in Arizona. If they'd have stood back, put a perimeter up, that's what they're doing with this. I'm going to ask the group, what do you do with that? Knowing what we know now about cell damage, knowing what we know now about how explosive the gas is and the chemistry of it. These are critical things to start talking about. Let's go to the next slide. So you put them in trucks, start getting bigger and bigger. So at this point, what we're looking at is a moving target. That, to me, that's what I try and talk to the fire department. Large storage is pretty simple in our world. It really is, compared to a moving target. Could be anywhere, under a bridge. If this starts burning, do you let it burn? What's the spalling doing to the concrete? You've got to start asking all these questions. Is that temperature start affecting the concrete of the bridge? If you have a large semi on fire, it's a moving target. It changes the game. When I teach solar farms and I teach large storage for the solar industry, it's pretty simple, guys. Everybody's on board. They pretty much get it. They understand it, and they've got solid strategies and tactics. This becomes a moving target. This is a lot harder to teach because the scenarios just go through the roof. Think about it. So to me, a lot of firefighters go, whoo, I just have a large storage on fire and not one of these, which basically, fundamentally, you teach solid strategies and tactics to a firefighter, and they understand the chemistry and the cell and the off-gassing on a large storage. It's not a problem. It may be a logistical problem in the sense of where you put that storage. It may be close to a residential area where you have to be consciously looking at sheltering in place and stuff like that. But outside of that, it's solid. Where's this truck parked in a community? You tell me. So let's go to the next slide. So you've got the EV trucks too. So everybody starts taking off-roading and they start banging those around. What's the damage? What's the mechanical? I can see the wheels turning in the firefighters when they start thinking about mechanical damage in that cell and that separator. And you got an anode and cathode and the trauma to that cell. You've got to start fundamentally asking those questions. Let's go to the next slide. So solutions. Number one, solid strategies and tactics for large storage. I love teaching large storage to firefighters. Get down to the nitty gritty. If the thing is in a box and it's off gassing or burning and those are collecting, stay away from it. Be respectful for that, okay? But again, if it's out and you've got these containers with the cell and with the module, there's a lot of them in there and they're 5-10 feet apart. Guess what? You let the one burn and you start working that. So solid strategies and tactics, same with a solar farm. You can start looking at putting water and understanding the DC arc on a solar farm, not going into a solar farm, connected to storage, but you're looking at rapid shutdown too. You're looking at full protection. So for cars, this is what they're doing in England. I want to share what they're doing. This is called an EVCU. It's an electric vehicle containment unit. And how it works is when they have EV fire in England, they pull one of these units out and it's run by the towing company, John Beach Towing. And what they do is they pull this unit out and the EV gets pulled into this unit and it has a sprinkler system so it doesn't submerge it in water, which they don't want you to do correctly. What it does is it just cools it down below basically off-gassing temperature and thermal runaway. And it has a sump pump with a filter and it just circulates water and it's cooling the cell down as much as possible. And it's like a washing machine, but it's not standing in water. And they're using these very, very successfully. This is what I'm seeing used in Great Britain right now. If you go to the next slide, it's just part of their standard response. I'm looking at trying to have fire departments look at these units that are available. Now, again, their structure in England is a little different because they're more larger fire departments and it's easier to implement. And so this is kind of like a standard operating procedure, but these EVs get put into these containers and it's a containment unit. It does not solve the problem. It contains the unit till the battery can be looked at, till the battery can be identified as what went wrong, what was damaged, what went into thermal runaway. And most of them are open. So the off-gassing, if there is any hydrogen, it is basically off-gassing. And again, being aware of the off-gassing is so important, those fundamental things. So to me, I would say large storage with solar farms, strategies and tactics, understanding if you're covering real estate with solar panels connected to large storage, rapid shutdown is key. And trust me, it only takes one fire to show you, pencil that out. Absolutely key. Optimizers and microinverters for commercial on a building. Solar farm doesn't pencil out, but having the fire department understand the arcs, understanding the high voltage and understanding they can put water on the system from a safe distance and stop basically the arc fault from burning anything and stop, more importantly, the garage fire that's going to happen after the arc fault. And then with EVs, we've got a moving target. This is the discussion with the fire department. This is where it gets interesting. So I'm going to end there and we're going to go to questions, and I hope there's some questions and we can start working through this.
There are definitely some questions, so thank you so much for that. I'm going to jump right into it since we've got about 15 minutes here. Starting with some clarifications, we had people asking about the situations in which water should be used on fires. I know in the previous residential webinar last month, instruction was to cool the battery with water and then let it get to ambient air temperature. But can you maybe just provide some clarification about when water should not be used? Is it less about the size of the battery and more about the battery type?
Okay, great question. And that's where the 6-hour class comes in. So there's a big difference between a residential battery and large storage. Basically cells. How many cells are in there and what makes large storage residential and EV? So the reason we can put water on a residential battery is basically the amount of cells, the amount of reactivity, whether on fire, is not going, the water is going to be able to do its job. It's going to be able to put it out and cool it down. We can overwhelm a residential battery with water from like fire trucks. We can't do that on large storage. We don't have enough water to put on a system, number one. Number two, there's a much bigger reaction going on. Number three, there's a lot more chemistry. So it is to do with the amount of chemistry, the amount of cells, and also when you look at NMC and NCA, it's the toxicity of the heavy metals, and you don't want it getting in the water. You don't have to worry about it contaminating water, whether it does or not. But those are the reasons why a residential, put water on it, commercial, large storage, you don't want to put water. Does that clear that up?
Yeah, I think that was helpful. And then when it also comes to use of water, we had some questions about runoff. So if you're using water during containment, is that water, is the runoff getting into groundwater? If it has toxics in it, can you speak to any potential environmental impacts of using water on a large fire or an EV fire if that's different? Again,
that's where knowing the chemistry of that large storage is critical. If you know the chemistry is NMC or NCA, then there can be heavy metals in that. And so we don't know for sure the contamination because there hasn't been a study of direct runoff. They've done some studies, but at this point, the potential for some runoff and the potential for heavy metals is there. So basically, you're talking kilograms. Like in a Tesla Model 3, there's a kilogram of basically electrolytes, heavy metals in there. So at this point, what we're looking at is, do we have runoff? I would say that that's why they let cars burn. And again, we don't have enough water. So think of it like this: on large storage, don't think about the runoff as in contamination. Think you're just going to make the situation worse by putting more water on it. And so if you really want to think about trying to contaminate water, continue down that path of putting water on that large storage. Whereas if you use your water sensibly for exposure protection, there is no contamination. That's the key. If you use your water smartly for exposure protection, there's no contamination. Let the storage burn. That's the critical thing to understand.
And then in terms of the burning and the smoke from the burning, we've had some questions also about potential health impacts to surrounding communities. I'm not sure if there have been any studies or if we really have that information quite yet on any human respiratory issues that can come up from the smoke. I know you talked a little bit about sheltering in place and making sure that you know which way the wind is going so the fire doesn't blow towards a community of people. But can you speak a little bit more about the potential respiratory or health impacts?
Yeah, I've been on several tire fires in my career where a tire recycling plant's gone up and the plume of smoke is just toxic, completely black and toxic. And what we've done is shelter in place. We've got to understand that with these communities, and if this large storage is in a community and the smoke is going, we have shelter in place SOGs for that tire fire. It's the same thing. We can't get caught with saying, is there toxicity or not? Yes, there is a toxicity. So train for shelter in place. And it's the same health indicators as if there's a large tire fire or there is a large transformer fire or any large building fire. That smoke is toxic. And what we've got to do is protect civilians with shelter in place. So to me, the key is this is not a new event for a fire department. This is an event that most firefighters have had, use the same strategies and tactics with shelter in place.
When it comes to preparation from fire departments and having that information before this happens, how can a fire department identify batteries or battery chemistry without advanced registration of units if they just show up somewhere? Like what kind of information or what can they do to be, I guess if they're not prepared, how do they know what equipment to bring or use if they don't know in advance that there's a battery there? So I think just maybe kind of speaking to what fire departments can do to prepare and what should happen if they haven't had this type of training and they're dealing with a battery fire.
So I would say working with the solar industry, and basically I'm going to be working with Pivot Energy tomorrow. I'm going to be flying to Colorado and working and teaching fire departments. But what I would say to firefighters is 70% of firefighters in this country are volunteers still. So they're not paid. So basically what I would say is the solar industry wants them to reach out. The one thing I think I've surprised most fire departments with is if I tell them to reach out to the solar industry and to reach out to the developers and say, what do you put in? What is the chemistry? And have the questions in this webinar. Start writing a cheat sheet. If you're a chief listening to this webinar, start writing those questions out. Go to a developer, ask them, what's the chemistry? What kind of smoke would this produce? Not, it's never going to happen. Say, okay, we get it. It's going to be in our community, but it may happen. It may happen because of mechanical, thermal, electrical abuse. It may be a dendrite. Write those out and say, can you answer these questions? Give me some guidance. That way they can start putting together and start working directly with the installers, with the people developing this. I want that connection. I want to arm the fire service. And if you go through this webinar, trust me, you'll have a lot of questions that you'll need filled. And that is the key to this webinar.
So as the large battery storage market matures and these batteries become a lot more common, can you maybe compare the risks to firefighters, dealing with a large battery storage fire, or, rather stationary or EV compared to large propane or diesel tank fires?
Yeah. So I remember in 1990 when I became a firefighter, we did the propane gas burn. And everybody who's a firefighter knows what I'm talking about. We've been training with diesel fires. We've been training with gas. We've been training with electrical fires for years. We haven't been training with solar and batteries. That's the difference. In 50 years from now, 70 years from now, it's just one of the things that we trained on. But it's a new thing. So at this point, we have to be actively training on it. This is a new technology. It's in our communities. So I'd say that's the difference is we've got training for a solid propane fire, for diesel fire, for electrical fire, transformer fire. We don't have solid strategies and tactics for those other, and that's what we need to develop.
Sorry about that. I muted myself. We've got thunder and lightning here. But in terms of UL certifications, we had a question about specifically 9540A UL certification. Is this something that's required in certain states, or is it largely voluntary for utility scale storage states to undergo or adhere to certain certifications? And if you know anything about this certification, does it require cell and module testing?
So what I've done is a lot of research on the residential, and it's basically you've got the cell, you've got the module, and you've got the unit itself. And there's been extensive testing with that. And a lot of my mentors actually replied to a lot of questions like this on LinkedIn and said, listen, there is very, very little basically testing of a large battery that has not, UL 9540 does not do that. So that's the next thing that I think is going to be of interest of testing. Okay, we don't have testing on those. There's a couple of companies who have just done some tests, but we can give you the information for the cell and the module. And to me, if it's the same cell that's in a residential battery as a large storage, take that information of the cell, the off-gassing, the thermal runaway, and use that information and just build out a larger model. That's all. It's not there yet. They haven't done those full testing for the large storage.
We also had some questions about new technologies and tools that fire departments might be able to use with batteries. Questions about liquid nitrogen being used to stop thermal runaway and off-gassing, and also about a gel being used for large-scale storage fire containment. Can you speak a little bit more about that? And if so, how can a fire department access training for new tools and technologies for fire mitigation on these types of fires?
So I would say the Fire Safety Research Institute is a brilliant platform for anyone to go to see about new tools and new technique, because they're tools. They're not solutions. They're tools. The fire blanket is a tool. It's not a solution. And the Fire Safety Research Institute has done a bunch of testing, again, about gels, about how to put a fire out, an EV fire. Is it effective with water, without water, large storage? Fire Safety Research Institute, that's their job, is to do this research and to give the fire department information. So please start there. They do fantastic work continuously on this. And I think that is the major resource that I point everybody to. It's wonderful for them to be there doing what they do.
Yeah, I think that's helpful because we've had a lot of questions about, different resources and tools specifically for, fire and building departments that are looking to, permit large battery storage. So all of that is super helpful. I want to ask a question about kind of post-fire, and if there's any kind of protocol or process for after a fire happens. Is there still any risk associated, after everything has been put out?
Well, with the EVs, what we're saying is the fire isn't out till that battery is removed, till the cells are removed, till the module's removed. So no, it's not. There's a lot after the incident, a lot after the flames go out. With large storage, by that time, the technical team have got there. You've got to remember there's a gap. You've got the fire department response. They do a good job. They contain it, protect exposures, shelter in place, mitigate the incident, stabilize it. That's when the experts come in. So large storage is completely different than an EV, because an EV is left on scene. There isn't a technical team coming out at 3 a.m. in the morning to look at your EV. It just isn't happening. But if you have large storage in your area, the actual people that own that storage, they will be notified and there will be a team there. That's what the fire department's job is, to turn up, know what to do, to stabilize it. Solid strategies and tactics. Don't make drama. Get it done. Protect your civilians, and then let the experts. With an EV, whoop, that's not happening. So that's where I say, and an EV is not done till it's not done, till the batteries removed, till the modules are removed, till the cells are removed.
Is there a risk of reignition after the initial fire is stopped burning? How long does a battery generally burn for?
So depending on which battery you're talking about, let's say a large storage battery. I think if the fire department can keep the water off the burning and actually concentrate on the exposures, you're looking at a full burnout of the cells, especially at the temperatures of each cell releases. You're talking at a very, very comprehensive burn where it burns all the material in that one box. The job is not to cascade it. So critical use of water to protect exposures on that is critical. But outside of that, for an EV, good luck. You put it out, you cool it down. I can't tell you. There is no way of knowing if that thing, because it's in a metal box, it's sealed. We have no idea what's going on in there. They've got to take it out. They've got to remove the modules. They've got to remove the cells.
Okay, yeah. Well, we're just about out of time today, and I apologize that I wasn't able to get to all the questions. I think we kind of spread the questions around to a variety of different topics, but maybe you can leave us with a few words of how folks can reach you and what kind of training that you can provide, and to who.
Yeah. So number one, Fire Safety Research Institute. Amazing. This is what those guys get paid to blow stuff up. Is brilliant. And they get really, really good results. They get so much information. Use them. Go straight to them. Start looking at the tools, what's out there. For me, I do a strategies and tactics. I take the drama. The idea is to get in there, to look at what you've got in your area and do strategies and tactics. So not reinventing the wheel. This is a new technology. It's in our neighborhood. We have all these different technologies in our neighborhood. This is just one more. Let's look at it. Let's understand it. Let's apply good discipline, strategies, and tactics to mitigate our part of the solution. And that's what I would say is start thinking about developing strategies and tactics for this instead of a discussion. Start putting the questions on paper and start answering your own questions with solid fact.
Thank you so much, Captain Burt. Again, you can reach out to Captain Burt at solarandfireeducation@gmail.com if you have specific questions about the trainings that he offers. Thank you to everyone who stuck around today. I'm going to pass things back to Zareen.
Thank you.
Thanks everyone again for joining. We have a couple of upcoming webinars. There is one next week on July 17th and another one on July 21st about load growth. And if you would like to register for either of these or learn more, you can do so at cleanegroup.org/webinars. I'll put it in the chat, and it will also be in the follow-up email that will also contain the recording of today's webinar. So thanks again, everyone, and have a great afternoon.